Hi, everybody. This is Jim Corkins, and we are starting the new section on energy. So please go ahead and start the reading. It's whatever class you're in. It's going to be in Coletta and OpenStax in the same textbook, Chapter 7. Okay? So in this video, what we're going to do is we're going to talk about the origins of energy. Okay? So what energy is it's essentially another view of the universe aside from Newton's view, where Newton sees everything in the universe as vectors and things like that. But there's another view and this view is energy. It's responsible for objects moving. It's a process, not like a vector or a thing. We can observe it when it's changing from one thing to another. Okay, so there's a transformation happening, and it does have a conserved quantity to it. So if you are, a lot of you have probably already taken your chemistry courses. So energy is heat. So chemists often look at the work output, which is how physicists refer to heat, is we refer to it as work. And that would be energy coming from out of leaving the system or entering in the system. Okay. Now, we'll talk more about what work is and later on. Now, who created the concept of energy? Well, that came from Gottfried Wilhelm Leibniz. Now, he was developing this concept following Newton's work. Okay, and so Descartes, who was a buddy of Newton, was arguing that everything in the universe had to do with mass and velocity, right? And basically that they were vectors. Now, Leibniz asserted that this was not necessarily true, and he argued that the universe could be seen as mass times velocity squared, which is more of a scalar quantity than a vector quantity. So you have like almost two different camps. It's kind of interesting. It wasn't until Coriolis came along that we found out that this mv squared is actually 1/2 mv squared, and that is the kinetic energy of objects. Okay, and we'll learn about that in a second. But Coriolis is who is responsible for taking Leibniz work further and started actually quantifying things and actually accurately measuring what energy is. So these two individuals, one created it and the other one took it further and was able to quantify it and make it more accurate. Okay? So how was it actually derived? Coriolis is the one who is responsible for the modern day concept of energy. Okay? Where Coriolis realized in order for an object to change its speed, you need a force working on something across a displacement. Okay? And so if you graph force versus displacement, the area underneath that curve, that is going to be the work done on the object, and that will be what is responsible for speeding an object up or slowing it down. Okay, the units for energy and work are is 1 joule, and 1 joule is 1 Newton meter. If you've taken chemistry, that you probably deal more with calories or kilocalories. So if you read like a side of a cereal box, on the side, those are kilocalories, which is 1,000 calories, which is let me see. So 1 calorie is 4.184 joules, and 1 kilocalorie is 4,184 joules. Okay, so those are how chemistry and physics are related. We're still using the same thing. It's just we're looking at it from two different perspectives. Joules is more useful in physics, though, okay, which is a Newton meter. So you've probably heard about different types of energy. One is potential energy and one is kinetic energy. And how were they derived? Okay, and what we're going to find out is essentially work is the change in kinetic energy, and that force across that displacement, that area underneath that curve, which is responsible for the change in velocity, which is then the change in kinetic energy. So we're going to find out how that works. And then we're going to look at what is potential energy and how where this area underneath that curve is also equal to the negative potential energy. All right. So how did Coriolis derive energy? Basically, the modern interpretation of kinetic energy. So starting with work, okay, where a force over a displacement is equal to work, but a force is equal to mass times acceleration. So he did use Newton's work to help him refine the concept of kinetic energy. So when we're looking at this, what you find out is we have work is equal to mass times acceleration dx. Now, where acceleration is the change in velocity over change in time. And so you could do a part and partial derivative where you take the change in velocity dx, which is times an actual velocity, which is dx dt. So what you find out is that dv dx is equal to that velocity, since this part is just velocity. So moving that velocity to the front, what we find out is acceleration can be seen as a velocity times the change in velocity over the change in displacement. So if we put this back in here, what you get is this. And then the dx's will cancel themselves out, and what you have is mv dv. Now we're going to integrate the velocity through over the change in velocity. And when you do that, when you integrate that, you get 1/2 mv squared from the initial velocity to the final velocity. Well, plugging those in for that velocity here, that velocity unit, you get 1/2 m delta v squared. And 1/2 m delta v squared is the kinetic energy. Okay, so that's how Coriolis created that the equation for kinetic energy. Now, moving on, how was potential energy derived? Okay, so if you look on the left, right over here, if you have a ball and you're at a height h and you drop it, okay, well, that ball is going to start speeding up as its height decreases, okay, until it reaches its maximum velocity right before hitting the ground, okay, which is kind of weird in the fact that its initial position is actually a higher number than the final position, okay. So when I integrate, you always want to integrate from low to high, right, low to high. But in this case, where it started is actually the high of that, okay? So work is equal to the change is equal to the change in position for times the force, okay? So what we're going to do is we're going to take that right here and we're going to sub in mass times acceleration. Well, in this case, the only acceleration here is gravity, okay? So when you integrate this, and there is no y in here, there's no y variable, when you integrate that, you just get mgy going from the low height, height of 0 to the height of 1 in this case. Well, that's mg times y initial minus y final. And then if you take out if you multiply through by a negative right here, you could switch these two things around to become this. And then what you find out, if you keep that negative in front, negative mg is equal to the change in y, which is the change in height. So you find out that negative mg delta y, which is potential energy, well, then work is equal to a negative delta u. So it's the opposite of the kinetic energy. So there's a yin-yang between kinetic energy and potential energy. Where kinetic energy is high, potential energy will be low. And where potential energy is high, kinetic energy will be low. All right. There is another potential energy. This potential energy due to gravity is basically it's the energy of height. Okay. But there is another potential energy. And so when you have a spring, well, just like with potential energy due to gravity, when you throw a ball up in the air, it doesn't matter whether it's moving up or down, to the right or to the left. When you throw a ball up and it's in free fall, it doesn't matter the path of that object. It doesn't matter the path that object takes. Gravity is still going to be pulling straight down on it no matter what. Well, similar to this, you have a spring. Okay, so when you compress or stretch a spring, it doesn't matter whether you're pushing on or pulling on it. That spring is going to be acting on you with a force, with that restorative force, no matter what. So in this case, let's say you start off and you've compressed a spring, and then you let it go. It's going to want to snap back to its equilibrium position. So that's that restorative force that we talked about back in forces. So this is another type of potential energy, because no matter what, whether you pull it or push it, stretch it or compress it, that spring is going to want to restore back to the equilibrium position. Okay. So what you find out is, again, if you started out here where you have your initial position is higher than the final position, which is 0. So starting out there, you have we're going to go ahead and sub in the force due to a spring, which is k times x, and then we're going to go ahead and integrate that. Well, when you integrate it, you have an x here. You're going to get a 1/2 x squared times m. Okay, and since we're integrating from low, which is in this case x final, which is going to be 0, and x initial was some distance away from that, okay, you're going to get 1/2 x initial minus x final squared. Well, when you flip those two things, okay, when we have to flip those two things, you have to bring that negative to the front. And what you get, again, is you get another type of potential energy. Okay? In this case, this potential energy is due to a spring. Again, potential energies are path independent. They don't matter which way, where the object is. It's going to be pulling on it no matter which way the object is moving. It's independent of the path, and it's always going to be pulling on that object. We'll get more into that. We'll get more into that in the next section, okay? But this is where how energy was derived, okay? So I thought you needed to know where it came from, okay? All right, so in 5.1, the next section, we'll get into more about what these energies are, what they represent, and again, how potential energy is independent of path. So we'll get into kinetic energy, potential energy, and also work. All right, thank you very much.